Alright guys, this is my first video ever. I want to present a unique method that I have not been able to find anywhere on the internet of finding the function that gives you the sum of perfect squares. There are a plethora of different proofs posted online. Some of them are algebraic, some of them are visual proofs. They're all very original and creative, but this video will be using calculus and linear algebra for the proof. So before we start the actual video, I want to go over the prerequisites to understand this video. You're going to need some basic calculus knowledge of derivatives, antiderivatives, how the power rule works, and how to undo the power rule within polynomial functions. Higher order derivatives, so derivatives of derivatives, x to the third, to the fourth, to the fifth power, and then at the end, lots of linear algebra and solving systems of equations. Alright, so the first thing that I did was try to understand how the rate of change is behaving. The first thing I did was I plotted the function out with the average rate of change in the far right column. We know that the rate of change itself is increasing, and we know that the rate of change is going to be perfect squares, since that is by definition what we're adding. So this is where the understanding of rates of change come into play. The new column that we can see here all the way on the far right is telling us how the rate of change is changing quantifiably. It's clearly increasing, but at a constant rate, as we can see, going from 5 to 7 to 9 to 11. Alright guys, I promise this is the last section that has anything to do with rates of change of rates of change of rates of change. The third order derivative of this function is simply a constant 2. From here we can work backwards. What we know is we have a third level derivative, which is 2. Working backwards we can get the second level derivative, which is 2x plus a certain constant. From there we get the first derivative in terms of x squared plus a constant b plus ax plus c. Now b and c we can just combine into one constant. And then once we take a step back one more time, we actually get a certain function value. X to the third over 3 plus ax squared over 2 plus dx plus e, whereas we have a, d, and e, three constants that we don't know of. Now, although conceptually systems of equations might appear easier to grasp than calculus, linear algebra with multiple fractions and 3 variables takes a lot of writing out. It's still very manageable. However, to make it easier on you, I allowed Symbolab to solve the system of equations neatly. It will find what the constants have to be in order to satisfy the function. I don't want you guys to think that I cheated, so here's a quick look at the math that I did to get the right answer. And now you see why I allowed a computer to do it. After all that calculus and linear algebra, we come up with a function that meets all the criteria to be the sum of n perfect squares. Just a quick note, the written form of this function is usually expressed as the following. So I wanted to do some quick algebraic manipulation to show that my function and the most commonly used sum function are identical. After some quick multiplication and application of the FOIL rule, and combining like terms, and finally dividing every single term by 6, we get the original function that I had come up with using calculus and linear algebra. Well, there you have it guys, a fairly straightforward and monotone method, although quite unique, of finding a function based on its sums. This is my first video ever, and would appreciate any feedback on this video, and would take any suggestions for future videos. So thank you for watching, maybe subscribe, see you guys later.